Hi, I'm Dan Lugar. I'm a staff member here at IDA. I'm filling in for John Richie, who couldn't be here today. He's a cadet at the Air Force Academy. So my talk today is about machine learning for efficient fuzzing. When I talk about fuzzing, it's about software testing. So running random inputs, checking the outputs, checking if there are faults in the outputs. If there's faults, that implies that there's a bug in the software. Okay, so sulfur bugs are important to study because they have catastrophic consequences. So, for example, this example with Mariner 1, the omission of a hyphen from the guidance program resulted in the rocket veering off course and needing to be destroyed. So the entire mission was basically compromised because someone fat-fingered their program. And then also here, according to a report by the Consortium for Information and Software Quality, poor software quality had an estimated cost of $2.08 trillion to the US economy in the year 2020. And that's costs due to software bugs as well as cybersecurity vulnerabilities due to poor software construction. So what was our goal in this research project? So our goal was to develop a software fuzzer based on machine learning. So what is fuzzing? Fuzzing is just running random inputs through a software program, checking the outputs, checking if they're the right outputs. If they're not the right outputs, you know there's a bug in the program. And the goal of testing the software is obviously to fix bugs prior to deploying the software system. As you can imagine, this can be a very difficult problem. So, or a very computationally intensive problem if you're trying to run every combination of possible inputs through the program. So, for example, consider a program that has 20 inputs to it, 20 binary inputs. The number of possible combinations of inputs would be 2 to the 20th power, which is over 1 million. So it just becomes infeasible to test every possible combination of inputs to look for a faulty output. So what people resort to is just randomly running random inputs into the program and just hoping that if there's a bug, that they catch it. The goal on our end was to use machine learning to learn about the inputs to a program that trigger bugs so that we can focus our search of that space of possible inputs around those inputs that trigger bugs. So hopefully we can uncover more and more inputs that trigger bugs. And then we'll have a huge list of inputs that trigger a fault. And then we can learn about that fault so that can inform the software developer where to look for the fault in the program. So our algorithm-guided approach is as follows. We first run a batch of randomly generated inputs through the program and compare those inputs to an oracle. So the oracle will tell you whether the output is the expected correct output or not. If the output does not match the oracle, it's considered a fault triggering input. Then we train a binary classification model on the input string values and the fault or no fault status of those inputs. And then we compute each variable's contribution to the model's predictions of fault versus no fault. And that's referred to as the feature importance values of the inputs. We modify the most important features of the inputs to search for inputs that are similar to those fault triggering inputs, which can be thought of as being close to the fault triggering inputs in the input space. And then we run new input strings through the program and continue the cycle, adding to our training data set as we go and hopefully generating more and more fault triggering inputs. So I won't dwell on this too much because it is a speed talk, but we're using a gradient boosting decision tree as our binary classifier. And so you can kind of think of this as similar to a random forest algorithm where we have a bunch of little trees that are classifiers, and then they classify an input, and you take the classification ends up being whichever classification was voted on by the most trees. So this kind of cuts down on the overfitting problem that you get when you're just training a single tree. And then to determine the feature importances of the input variables, we are using Shapley additive explanation values or SHAP values, which is which is easy to use in a SHAP package in Python. The SHAP values approximate the average contribution of each of the features to the predicted output of fault versus no fault. We tested our approach on the traffic collision avoidance system, or TCAS system, that's on a lot of, or on all commercial airplanes. So what the TCAS program does is that it monitors the space, or it monitors the space around an aircraft and alerts the pilot if it's at risk of a mid-air collision with another aircraft. Then it provides a resolution advisory to avoid a collision. So the TCAS program has 12 input variables, which are a combination of continuous, categorical, and Boolean inputs. And it has one categorical output variable, which is either unresolved, upward resolution advisory, or downward resolution advisory. So we got a hold of this program. It's a C program. We manually introduced a bug into the program. So we can see that that no intent variable was changed from 0 to -1. And then we used our machine learning fuzzer to try to learn about inputs that trigger faults in the outputs due to that bug that we introduced into the program. So this is some of the results from our program. You can see that the machine learning fuzzer is able to generate, that's the yellow line on the top, is able to generate more faults, generate more fault producing inputs than just randomly searching that space of possible inputs. And in the bottom, we're able to see how the feature importance values are changing as we add more data to that training set. So you can see that the feature importance values of a lot of the variables are going up and down, but clearly variables 0 and 9 are dominating the rest. So that implies that they're the most important in this case in determining whether or not an input triggers a fault. So challenges in feature work. So one of the main challenges is that a software oracle has to be available to determine whether or not an output is faulty. So for certain cases, this might not be an issue if you're trying to replace a legacy software with new software. If you consider the legacy software as ground truth, then there's your oracle. In other cases, it's not as straightforward. Another one of the challenges on the machine learning side is that there are far fewer fault triggering inputs in the training data set than there are inputs that do not trigger a fault. So that's what's referred to as the class imbalance problem in machine learning. We're overcoming this by just trying different weighting schemes for the training data set. And then currently we are interested in how multiple bugs in a program affect the ability to rank the inputs by their feature importances. So the previous example I showed you, there was just one bug. We're interested in what if the program has multiple bugs, how does it affect your approach? And I think I'm at my time. So thank you so much for your attention, and I'll be out at the poster session afterwards if you have questions.